4 astronauts are hurtling through space right now on a mission that NASA insiders are calling the most dangerous human spaceflight in half a century. They're riding hardware that's barely been tested, protected by a heat shield that failed catastrophically on its first unmanned flight, and heading into radiation levels that could fundamentally alter their DNA. This isn't speculation or worst-case thinking. This is Artemis II, and it launched from Kennedy Space Center on April 1st, 2026. The crew includes NASA astronauts Reid Wiseman, Victor Glover, Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen. They're the first humans to venture beyond low Earth orbit since Apollo 17 in December 1972. That's 54 years of staying close to home, orbiting safely within Earth's protective magnetic bubble. Now they're out there, exposed to the full fury of deep space, testing systems that have never carried human lives before. What makes this mission so dangerous isn't any single factor. It's the convergence of multiple risks, each serious enough to warrant postponement on its own, combining into something unprecedented in modern spaceflight. And the decision to proceed despite these dangers reveals something troubling about how NASA operates under political and financial pressure. Let's start with the most visible crisis, the one that nearly derailed this mission before it left the ground: the heat shield problem. When Artemis I flew this exact trajectory in 2022 without a crew, something went catastrophically wrong during re-entry. Large chunks of the heat shield's AVCOAT material blew out, leaving deep gouges and divots across the protective surface. Over 100 locations showed damage far beyond anything NASA's models had predicted. The ablative material that's supposed to char and burn away in a controlled manner instead cracked and shed in irregular chunks, exposing underlying layers to temperatures that approach 5,000 degrees Fahrenheit. NASA kept this quiet for a while. It wasn't until May 2024, when the Office of the Inspector General released photographs, that the space community saw the full extent of the damage. The images were shocking. Deep holes penetrated multiple layers of the heat shield material. Some sections looked like they'd been hit with a sledgehammer. Former NASA engineer and astronaut Charles Kamada became one of the loudest voices demanding answers. Kamada knows spacecraft failure intimately. He survived the Columbia disaster in 2003, though 7 of his colleagues didn't. He's seen what happens when NASA convinces itself that known problems are acceptable risks. His assessment of the Artemis II decision is damning. He argues that NASA has built what he calls toy models, simplified simulations designed to produce the answer the agency wants rather than the truth. These models aren't grounded in actual physics, he says. They're sophisticated justifications for a predetermined conclusion that flying is safe enough. According to Kamada, NASA is flying Artemis II based on vibes. The agency is essentially hoping that whatever caused the heat shield to fail on Artemis, one won't get bad enough to kill the crew on Artemis II. That's not engineering. That's gambling with human lives. The technical explanation for the heat shield failure reveals why this is so concerning. During the skip re-entry maneuver, where the spacecraft briefly dips into the atmosphere, bounces back out, then dips again before final descent, something unexpected happened. Between those atmospheric dips, heating rates decreased. That sounds good until you understand what it triggered. Thermal energy accumulated inside the AVCOAT material faster than it could dissipate. The ablation process, which is supposed to carry heat away as material burns off, generated gases trapped inside the heat shield. Avcoat didn't have sufficient permeability to let those gases escape. Pressure built up internally. The material cracked. When it finally gave way, chunks of heat shield material liberated themselves violently during the highest stress phase of re-entry. NASA's solution: don't fix the heat shield, change the trajectory. Mission managers eliminated the skip re-entry in favor of a steeper, more direct descent profile. A Tiger team determined this modified trajectory would minimize char loss and provide adequate thermal margins. The spacecraft will come in hotter and faster, subjecting the crew to increased deceleration forces, but theoretically reducing the conditions that caused the original failure. Here's what makes this approach so troubling. If SpaceX's Dragon capsule or Boeing's Starliner returned to Earth with this kind of damage, NASA would ground the program immediately. The agency would demand a complete redesign and multiple unmanned test flights before allowing humans aboard again. NASA holds commercial crew programs to rigorous safety standards. But Artemis? Different rules apparently apply. The review team's report exists, but the publicly released version is so heavily redacted it's nearly useless. Former NASA engineers and astronauts have criticized this lack of transparency. When you hide your safety analysis from public scrutiny, you remove a crucial layer of oversight. Mistakes that might be caught by outside experts go unchallenged. This pattern echoes the organizational failures that preceded both the Challenger and Columbia disasters. In both cases, NASA had data showing serious problems. In both cases, institutional pressure to maintain schedule and budget led decision-makers to rationalize away risks. In both cases, the rationalization failed catastrophically. The heat shield isn't even the only life-threatening system flying with known problems. Orion's environmental control and life support system has never flown with humans aboard. Artemis 1 didn't carry a complete ECLSS because there was no crew to support. That means the system making its debut on Artemis 2 is responsible for keeping 4 people alive in the vacuum of space with zero flight heritage. During pre-flight testing, the ECLSS experienced multiple serious failures. A ventilation system controller failed, traced to a circuit defect in the motor controlling gas flow through the crew cabin. Identical valves exist throughout the system. Every single one had to be retrofitted to withstand excess voltage, a problem nobody knew existed until it manifested during testing. Deformed sealing material on ECLSS valves caused overboard leakage. A carbon dioxide removal control valve showed deficiencies that required redesign. These aren't minor glitches. These are fundamental failures in systems that have to work perfectly, or the crew dies. NASA's mitigation strategy reveals how serious these concerns are. The agency inserted a 24-hour checkout period into the mission profile. After reaching low Earth orbit, Orion will spend roughly a day testing the ECLSS before committing to the trans-lunar injection burn that sends them toward the Moon. This is essentially a go/no-go decision point in space. If major ECLSS problems emerge, the crew can abort and return to Earth relatively quickly. Once they burn for the Moon, that safety margin evaporates. They're committed to a 10-day mission whether the life support works properly or not. The practical consequences of ECLSS failure are straightforward and terrifying. The system is redundant, with backup components for critical functions. But in the extremely unlikely event of total system shutdown, the astronauts suddenly lose breathable air, fresh water, temperature control, and safe cabin pressure. Their survival suits can provide emergency life support for about 6 days. After that, they're on borrowed time. Even partial failures create dangerous situations. The crew has already encountered problems. During one test, they struggled to set up the toilet, dealing with a controller issue that required Christina Koch to troubleshoot on the fly. A malfunctioning toilet might sound trivial until you're trapped in a small capsule with 3 other people for 10 days with no alternative. The battery systems present another layer of risk that almost nobody outside NASA's engineering teams understands. In late 2023, abort scenario analysis revealed that Orion's batteries might not maintain required power levels during extreme abort situations. These aren't theoretical edge cases. These are the exact scenarios where battery performance matters most, when the launch is going catastrophically wrong and the launch abort system has to fire. Vibration testing discovered an even more disturbing failure mode. Under worst-case abort conditions, the batteries could physically disconnect from the spacecraft's electrical systems. That would render Orion unable to deploy its parachutes. Without parachutes, the crew capsule becomes a ballistic projectile that will impact the ocean at terminal velocity. Nobody survives that. The batteries are built by Eagle Pitcher Technologies, the same company that supplied batteries for Apollo. Those Apollo-era batteries saved the Apollo 13 crew when the fuel cells failed. After spending days cold-soaked in space, the batteries powered up when needed and brought the crew home safely. But that was different technology, different design requirements, different testing regimes. The fact that Eagle Pitcher made reliable batteries 50 years ago doesn't guarantee these modern units will perform under conditions they've never actually experienced with human lives depending on them. The power system overall contains multiple potential failure points. 4 solar array wings unfurl in space to generate 11.2 kilowatts of electricity. This system powers everything: battery charging, life support, avionics, propulsion controls, communications. If it fails, the spacecraft goes dark. During Artemis 1, the solar arrays actually generated more power than expected. Good news, right? Except one of the power conditioning units experienced an anomaly. Nobody's entirely sure why. A similar or worse glitch during Artemis 2 could cascade through the electrical system, potentially knocking out multiple critical functions simultaneously. The Space Launch System rocket that carried them to orbit brings its own set of unprecedented risks. SLS has flown exactly once before, on Artemis 1. That's the sum total of its flight heritage. 1 launch, 1 mission, and now it's carrying humans. Compare that to the Space Shuttle, which flew 135 missions over 30 years, or the Saturn V, which flew 10 crewed missions before being retired. SLS went from first flight to crewed flight with no intermediate missions to identify and fix problems that only reveal themselves over multiple launches. The rocket is known to spring fuel leaks. During the Artemis 1 launch attempts, hydrogen leaks repeatedly forced scrubs. Ground crews developed workarounds, but those are band-aids on fundamental design issues. When you're loading supercooled liquid hydrogen and liquid oxygen into a rocket at enormous flow rates, you need systems that don't leak. Period. The Artemis 2 launch itself came within minutes of being scrubbed. One of the 2 batteries for the launch abort system showed an unexpectedly high temperature reading. The team determined it was an instrumentation issue rather than an actual battery problem, but that determination happened inside the launch window. If they'd needed 6 more minutes to troubleshoot, the launch would have scrubbed. There was also a communication problem between the Eastern Range and the flight termination system. This system can destroy the rocket if it veers off course toward populated areas. It's a safety-critical system that absolutely must work. The fact that it had communication issues during final countdown is not comforting. The launch sequence itself is a carefully choreographed moment of controlled violence. 4 RS-25 engines on the core stage ignite approximately 7 seconds before liftoff. The system confirms they've reached full power. Only then do the solid rocket boosters ignite at T0. Those solid boosters are critical to understand. Once they light, there's no shutting them down. They will burn until they exhaust their fuel. If something goes wrong after booster ignition, but before the rocket clears the tower, the launch abort system has to pull the crew capsule away from an out-of-control rocket that's producing over 7 million pounds of thrust. The boosters separate at roughly 3,100 miles per hour at an altitude of 30 miles. Until that separation, the astronauts are riding the most powerful rocket currently in operation, hoping nothing fails in a way the abort system can't handle. Right now, as the crew passes the point of equidistance between Earth and Moon, they're entering the most radiation-intensive environment humans have experienced in 50 years. And what we're learning is that we don't actually understand deep space radiation as well as we thought. But that's a whole different category of danger, one that doesn't just threaten the mission, it threatens the astronauts' long-term health in ways we're only beginning to understand. The radiation environment beyond Earth's magnetosphere is fundamentally different from anything modern astronauts have experienced. International Space Station crews receive protection from Earth's magnetic field, which deflects most of the charged particles streaming from the Sun. They're still within the planetary shield, even at 250 miles up, but the Artemis II crew crossed that boundary hours ago. Galactic cosmic rays are the first threat. These are atomic nuclei traveling at nearly the speed of light, stripped of their electrons, originating from supernovae and other violent cosmic events outside our solar system. When one of these particles slams into human tissue, it doesn't just damage the cell it hits. It creates a trail of secondary radiation as it passes through, affecting everything in its path. The particles are so energetic that conventional shielding barely slows them down. Adding more aluminum to the spacecraft might actually make things worse, creating more secondary radiation as the particles collide with the metal. Then there are solar energetic particles. These come from the Sun during solar flares and coronal mass ejections. A major solar storm can release particles with enough energy to deliver a lethal radiation dose in hours. The Apollo astronauts got lucky. They flew during a relatively quiet period in the solar cycle, except for one time. August 1972, between Apollo 16 and Apollo 17. A solar storm erupted that would have killed any astronauts in deep space. The radiation dose would have been catastrophic. If Apollo 17 had launched a few weeks earlier, the crew wouldn't have made it home. That's how narrow the margin was. That's how much luck factored into the Apollo program's success. NASA's Moon to Mars Space Weather Analysis Office monitors the sun constantly. They watch for flares, for coronal mass ejections, for any sign that a radiation storm might be building. When they detect activity, they share analysis with the Space Radiation Analysis Group. Together, these teams provide forecasts to mission control. But forecasting space weather isn't like forecasting terrestrial weather. The sun can erupt with minimal warning. The crew has procedures for solar particle events. They're trained to reconfigure the cabin, pulling stowed equipment from storage bays and positioning it to add mass between themselves and the incoming radiation. More mass equals more shielding. It's crude, but it's all they have. Testing this procedure is actually a major objective of the mission. They need to know how quickly they can set up this makeshift shelter, how effective it is, whether it's even practical in the confined space of the Orion capsule. Christina Koch will provide data we've never collected before. She's the first woman to fly in deep space. That's not just a historic milestone, it's a scientific necessity. We have exactly zero data on how female bodies respond to deep space radiation. The Apollo astronauts were all men. Space station crews operate inside Earth's protective bubble. Koch's presence means we'll finally understand how cosmic radiation affects different physiology, different hormonal systems, different cellular processes. The Apollo astronauts paid a price we didn't fully understand at the time. Multiple crew members developed cataracts later in life. Researchers traced this back to cosmic ray exposure. The high-energy particles damaged cells in their eyes, creating clouding that worsened with age. Many of them reported seeing flashes of light during the mission, brief streaks across their vision, even with their eyes closed. Those were cosmic rays passing directly through their retinas, exciting the optic nerve, creating phantom light shows as they slept. What else did cosmic radiation do to them? We're still finding out. Some studies suggest elevated cancer rates among deep space astronauts compared to their shuttle counterparts. The sample size is small, making statistical analysis difficult, but the trend is concerning. These men went to the moon for a few days. The Artemis II crew will spend 10 days beyond the magnetosphere. Future Mars missions could last years. Orion carries radiation sensors throughout the cabin. They're measuring dose rates in real time, tracking exactly how much radiation the crew receives and where it's coming from. These sensors feed data to mission control and to the onboard displays. If radiation levels spike, the crew will know immediately, but knowing doesn't equal protection. Their options are limited. Reconfigure the cabin, wait it out, hope the solar storm passes before the dose becomes dangerous. The spacecraft itself provides minimal shielding, aluminum hull, equipment racks, water storage. None of it is optimized for radiation protection, because optimizing for radiation protection would require mass the rocket can't lift. Every pound of shielding is a pound of other equipment you can't bring. Every inch of additional hull thickness is structural mass that cuts into your payload capacity. The engineers made trade-offs. They had to. But those trade-offs leave the crew exposed. Radiation affects more than just cancer risk. High doses can impair cognitive function. They can damage the central nervous system. They can affect motor control, memory, decision-making. These aren't theoretical risks. Studies on animals exposed to cosmic ray analogues show measurable neurological effects. If the Artemis II crew experiences a major solar particle event, they might face cognitive impairment during the mission itself, when they need their mental faculties most. The mission plan accounts for this, sort of. If radiation levels exceed certain thresholds, procedures exist to shorten the mission or modify the trajectory. But those procedures assume the crew remains capable of executing complex maneuvers. They assume the spacecraft systems continue functioning. They assume communication with Earth remains intact. Break any of those assumptions, and the contingency plans fall apart. Then there's the question of lifetime exposure limits. NASA sets career limits for astronauts based on radiation dose. The limits vary by age and gender because cancer risk changes with these factors. Every deep space mission uses up a significant fraction of an astronaut's career allowance. The Artemis II crew might not be able to fly deep space missions again. Their 10 days beyond the magnetosphere could be their only opportunity. That creates psychological pressure on top of the physical risk. This might be their one chance. They have to make it count. But here's what keeps the radiation specialists awake at night. We don't actually know how accurate our models are. The Apollo missions were too short and too infrequent to build robust statistical models. Space station crews don't experience true deep space radiation. The Artemis II crew is entering a regime where our understanding is built more on theory than data. We think we know what will happen. We believe our dose calculations are conservative. But belief isn't the same as knowledge. Cosmic rays don't just damage cells through direct hits. They create secondary radiation as they interact with spacecraft materials. A heavy ion slamming into aluminum produces a shower of particles, each capable of causing biological damage. The spacecraft itself becomes a source of radiation. Engineers call this the can of soup problem. Radiation hits the can from outside, but it also comes from the can itself as secondary particles bounce around inside. The Orion capsule is that can. The crew is the soup. During the Apollo 14 mission, astronaut Edgar Mitchell reported unusual fatigue and a sense of mental fogginess that he couldn't quite explain. He attributed it to the workload and stress. But later research suggested cosmic radiation might have played a role. High-energy particles affecting neural tissue, inflammation in the brain, subtle changes in cognitive processing that the astronauts couldn't identify in the moment but noticed in retrospect. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen are experiencing that same environment right now. They're moving through a radiation field that can penetrate metal and flesh. Their cells are absorbing energy from particles that originated in dying stars hundreds or thousands of light years away. Some of that damage will repair itself, some won't. We'll monitor their health for the rest of their lives, looking for effects that might take decades to manifest. The environmental control and life support system faces its own set of challenges, completely unrelated to radiation, but equally critical. ECLSS is what keeps the crew alive. It scrubs carbon dioxide from the air. It provides oxygen. It manages temperature and humidity. It's the difference between a habitable spacecraft and a metal coffin, and it's making its debut on this mission. Artemis I flew without a complete ECLSS. The spacecraft had basic environmental controls, but not the full system required for human occupation. That was intentional. Test the capsule first, add the crew later. Except now the crew is testing the ECLSS for the first time in the actual mission environment. There's no shakedown cruise, no low-risk checkout flight. This is the checkout flight. The system already experienced failures during ground testing. A ventilation controller failed during a pre-flight test for Artemis 3. Engineers traced the problem to a circuit in the motor controlling one of the gas flow valves. That same valve design is used throughout the ECLSS. Every single valve had to be hardened against excess voltage. Deformed sealing material caused leakage in other valves. A CO2 removal valve showed deficiencies that required redesign. These aren't minor glitches. These are fundamental problems with critical components. And while engineers fix the known issues, they can't test for unknown failure modes. The ECLSS contains hundreds of components, any of which could fail in ways that weren't anticipated during ground testing. Space has a way of finding weaknesses that don't show up in the lab. NASA built in a safety buffer. After reaching orbit, the crew spent 24 hours in low Earth orbit checking out the ECLSS before committing to the translunar injection burn. If major problems emerged, they could abort and come home. That checkout period has passed. The crew burned for the moon. They're committed. If the ECLSS fails now, their options are drastically limited. Total system shutdown would be catastrophic. The life support system has redundancy, backup systems, multiple layers of protection. But redundancy isn't the same as immunity. In the extremely unlikely event of complete ECLSS failure, the crew would lose breathable air, fresh water, temperature control, and safe cabin pressure. Their survival suits can provide life support for about 6 days in an emergency, 6 days to get home, 6 days for mission control to devise a solution, 6 days before the suit's carbon dioxide scrubbers saturate and stop working. Mission specialist Christina Koch already dealt with one ECLSS issue: problems setting up the toilet. A controller malfunction required troubleshooting in flight. She fixed it. But that incident highlights how even minor malfunctions can cascade into serious problems when you're operating a complex system with no access to spare parts or repair facilities. Everything has to work. When it doesn't, the crew has to improvise with whatever they have on board. The spacecraft's interior is smaller than most people imagine. Orion provides about as much habitable volume as a large SUV. 4 people, 10 days, in a space barely big enough to stand up in. There's no room for extensive exercise equipment, no space for privacy, no ability to escape your crewmates when tensions rise. The psychological pressure compounds the physical risks. Communication delays add another layer of stress. At their current distance from Earth, radio signals take nearly 3 seconds to make the round trip. Ask a question, wait 3 seconds for the answer. That might not sound like much, but try having a conversation with a 3-second delay. It's disorienting. It breaks the natural flow of dialogue. During critical situations when the crew needs immediate guidance from mission control, those 3 seconds stretch into eternity. And soon they'll experience something no human has felt in 50 years. Complete communication blackout. When Orion passes behind the moon, the spacecraft enters what NASA calls loss of signal. 40 minutes of complete radio silence. No communication with Earth. No telemetry streaming back to Houston. No ability for mission control to monitor spacecraft systems or provide guidance to the crew. The moon itself blocks every signal. Earth-based communication networks like the Deep Space Network can't penetrate 2,159 miles of solid rock. Even the experimental laser communication payload can't bypass basic physics. Signals don't pass through planetary bodies. This isn't theoretical. It's happening soon. Operationally, NASA calls the impact Significant, but manageable. That phrase does heavy lifting. Significant means mission control goes blind. They can't see what's happening. They can't track system performance. They can't respond to emergencies. Manageable means they've trained the crew to handle it. Pre-planned procedures, automated systems, trust that everything will work as designed. But spacecraft have a way of choosing the worst possible moments to malfunction. During those 40 minutes, the crew operates independently. They're trained for it. They've rehearsed the procedures. They know what to do if problems emerge. But training and reality diverge in subtle ways. The simulator never quite captures the psychological weight of being completely cut off from Earth while traveling at thousands of miles per hour around an alien world. Apollo crews experienced this same isolation. They described it differently. Some found it peaceful. Others found it unsettling. All of them noted how profoundly alone they felt when Earth disappeared behind the lunar horizon. Jim Lovell, who flew to the moon twice, said you could feel the weight of that silence. It pressed against you. The blackout begins when Orion reaches lunar occultation. The spacecraft slips behind the moon's eastern limb. Radio contact cuts off mid-transmission. Whatever the crew was saying to Houston ends abruptly. Whatever Houston was telling them stops without warning. Then silence. 40 minutes might not sound long, but consider what can happen in 40 minutes. Systems can fail. Trajectories can drift. Medical emergencies can develop. Fires can start. The crew has to handle everything themselves with only the resources on board. NASA emphasizes crew training for exactly this reason. Artemis II astronauts train to operate independently during loss of signal. They rely on pre-planned procedures and automated systems. The spacecraft's computers continue running navigation and attitude control. Life support keeps functioning. But if something unexpected happens, if a scenario arises that wasn't anticipated during training, the crew has to improvise. No second opinions from mission control. No consulting with engineers. No real-time data analysis from ground teams. Just 4 people in a spacecraft the size of a large SUV, traveling around the far side of the moon, making critical decisions on their own. Communication delays complicate things even when contact exists. Artemis II has taken humans farther from Earth than anyone since 1972. That distance creates signal lag. 3 seconds round trip. Ask a question, wait 3 seconds for the answer. That delay breaks conversational rhythm. It makes real-time troubleshooting nearly impossible. Try diagnosing a complex technical problem with 3-second gaps between each exchange. The flow of information fragments. Context gets lost. Misunderstandings multiply. During critical situations, when seconds matter, 3-second delays stretch into eternities. The crew already experienced communication failures. 50 minutes into the flight, NASA reported temporary loss of communication with Orion. The issue resolved quickly, but the reason remains unclear. Roughly 51 minutes into flight, during a planned handover between communication satellites, there was partial loss of signal. These glitches happened close to Earth, with full deep space network coverage. What happens during loss of signal when there's no backup? When the moon itself blocks every signal path, the spacecraft's position compounds the isolation. Right now, Orion is past equidistance between Earth and Moon. They're farther from home than from their destination. Point of no return has already passed. They're committed to the lunar flyby. They're committed to swinging around the far side. They're committed to those 40 minutes of complete isolation. Monday brings the flyby itself, closest approach to the lunar surface, the moment when they'll skim past the moon at the exact altitude and velocity calculated months ago. Timing has to be perfect. Trajectory has to be precise. Any deviation could send them on a path that misses Earth entirely on the return. During Apollo 13, the crew faced exactly this problem. They weren't on a free return trajectory when the oxygen tank exploded. They were on a hybrid trajectory designed to take them to Fra Mauro. That trajectory would slingshot them around the moon, but miss Earth by 2,600 miles on the return leg. Missing Earth by 2,600 miles means dying in space. The capsule would loop back around Earth and Moon repeatedly, taking 39 days before finally intersecting with Earth's atmosphere. By then, the crew would be long dead. Mission Control had to recalculate everything. They had to write new software for the guidance computer. They had to devise a burn using the lunar module's descent engine to shift Apollo 13 back onto a free return trajectory, a 34.23 second burn. Mathematical precision under extreme pressure. Artemis 2 uses a similar free return trajectory as a safety feature. If the main engines fail, the moon's gravity will naturally bend their path back toward Earth. A built-in safety net. But free return trajectories have limitations. They only work if you're already on that specific path. Deviations require correction burns. Correction burns require working engines. Working engines require functioning fuel systems and electrical power. The Apollo 13 crew got lucky. Their lunar module still worked. Its descent engine could provide thrust. Its batteries had power. Its guidance system functioned. They could execute the burn needed to get home. Artemis 2 has no lunar module, no backup spacecraft. If Orion's main engine fails, they're dependent entirely on the free return trajectory working exactly as calculated. No margin for error, no second chances. The mathematics behind free return trajectories allow no sloppiness. Every variable matters. Launch timing, translunar injection burn accuracy, mid-course correction precision, lunar flyby altitude, velocity at closest approach. Each parameter affects the return path. Small errors compound. A trajectory that should bring you home can instead send you past Earth into solar orbit. Apollo missions carried slide rules and paper charts for backup navigation. Artemis 2 relies on computer systems. Those computers are more sophisticated than anything available in the Apollo era. They're also more complex, more points of failure, more ways for software glitches to cascade into serious problems. During Artemis 1, one of the power conditioning units experienced an anomaly. The power system generated more electricity than expected, which sounds positive until you consider what an anomaly means. Unexpected behavior, something happening that wasn't predicted by pre-flight analysis. The system worked, but not the way engineers anticipated. That anomaly got flagged for investigation. Engineers studied the data. They developed theories about what caused it, but theories aren't certainties. And Artemis 1 flew without crew. If a similar anomaly occurs during Artemis 2, 4 people are depending on that power system continuing to function. The solar arrays generate 11.2 kilowatts. That power runs everything: battery charging, life support, avionics, propulsion systems, communications, thermal control. Lose power and you lose the spacecraft. Batteries provide backup for limited duration, but batteries drain. Silver zinc batteries like those that saved Apollo 13 can handle cold soaking in space, but they can't provide power indefinitely. Eagle Pitcher Technologies built Orion's batteries, same company that built Apollo 13's batteries. Those batteries spent days cold-soaked in space after the fuel cells failed. When the crew needed to power up the command module for re-entry, those batteries delivered. They provided just enough electricity to run critical systems during the final hours. But Apollo 13's batteries were designed for exactly that scenario. Orion's batteries faced different challenges. Abort scenario analysis in late 2023 revealed potential problems. The batteries might not maintain required power levels during extreme SLS abort profiles. Eagle Pitcher had to rebuild and requalify the units. Vibration testing found another issue. During worst-case abort scenarios, the batteries might disconnect from the capsule's electrical systems. That would render the spacecraft unable to deploy parachutes, unable to splash down safely. This represents a fringe scenario requiring both SLS failure and the most extreme vibrational environment possible as the abort motor fires. But fringe scenarios happen. Columbia and Challenger proved that unlikely failures occur. The launch abort system sits atop Orion like a 44-foot tower of rocket motors. Abort motor, attitude control motor, jettison motor. 3 motors working together to pull the crew capsule away from a failing rocket. If something goes wrong during launch, milliseconds matter. The abort system can activate and carry astronauts to safety within seconds, but that system already showed problems. During pre-launch checks, one of the 2 batteries for the launch abort system registered an unexpectedly high temperature. The Artemis II team determined it was an instrumentation issue, not an actual overheating battery. They cleared it as a non-constraint for launch. But temperature anomalies in batteries are never trivial. Thermal runaway in battery systems can lead to fires, explosions, catastrophic failures. They launched anyway. The temperature reading stayed out of range. The team decided to proceed. The launch window was narrow. Political pressure was immense. Schedule pressure was crushing. They made the call. Launch almost scrubbed for a different reason. Communication problems between the Eastern Range and the flight termination system. That system can destroy the rocket if it veers off course. It's a critical safety feature. Without reliable communication to the flight termination system, you can't launch. The problem resolved just in time. How many close calls does it take before luck runs out? The crew survival suits provide another layer of protection. Orion Crew Survival System suits. Custom fitted to each astronaut, they provide breathable air while removing carbon dioxide. They can keep astronauts alive for up to 6 days in emergencies, 6 days of life support if cabin pressure fails, 6 days if the ECLSS shuts down completely, 6 days to get home. The crew tested their suits extensively, leak checks, seat entry simulations, mobility assessments, eating and drinking while suited. The suits protect during dynamic flight phases. They provide life support if the cabin depressurizes. They offer survival capability after splashdown if recovery forces are delayed. But 6 days isn't long. Not when you're traveling to the moon and back. The mission timeline spans 10 days. If something catastrophic happens early in the mission, 6 days might not be enough time to get home. The suits buy time. They don't guarantee survival. Reed Wiseman commands the mission. Veteran astronaut. Former Navy test pilot. He's flown to the International Space Station. He's conducted spacewalks. He knows spacecraft systems. He's trained for emergencies. But he's never flown beyond low Earth orbit. None of the crew has. Victor Glover serves as pilot, another veteran, former Navy aviator. He flew the second operational SpaceX Crew Dragon mission to ISS. He's logged time in space, but not deep space, not outside Earth's protective magnetosphere, not in the radiation environment they're experiencing right now. Christina Koch, mission specialist. She holds the record for longest single spaceflight by a woman, 328 days aboard ISS. She's conducted 6 spacewalks. She's dealt with equipment failures in orbit. She fixed the toilet controller issue already on this mission. But ISS is 250 miles from Earth. Help is hours away. Artemis 2 is thousands of miles from Earth. Help is days away. Jeremy Hansen represents the Canadian Space Agency, rookie astronaut. This is his first space flight. He's a former CF-18 fighter pilot. He's trained extensively for this mission. But training and reality diverge. Space has a way of revealing gaps in preparation. 4 people, 4 different backgrounds, 4 different skill sets. They're trained to work as a team. They've spent countless hours in simulators. They've rehearsed procedures until they could perform them in their sleep. But they've never faced real emergencies in deep space. No one alive has. The last humans to fly beyond low Earth orbit were Eugene Cernan, Ronald Evans, and Harrison Schmitt aboard Apollo 17 in December 1972. That was 54 years ago. Everyone who flew to the moon during Apollo is either elderly or dead. Their experience is valuable but dated. Spacecraft technology has changed. Mission profiles have evolved. The institutional knowledge that got Apollo crews safely to the moon and back has largely been lost. NASA had to rebuild that knowledge from scratch. They studied Apollo mission reports. They interviewed surviving astronauts. They reverse-engineered solutions to problems that Apollo crews faced. But reading about an emergency is different from experiencing one. Hearing stories about radiation exposure or communication blackouts or navigation challenges isn't the same as confronting those realities yourself. Artemis 2 is relearning lessons that were learned 5 decades ago. Some of those lessons will be relearned the hard way. The mission clock ticks forward. Each second carries them deeper into territory no living human has traversed in over half a century. Mission Control in Houston monitors telemetry streams, hundreds of data points updating continuously, temperature readings, pressure levels, power consumption, radiation exposure. Everything appears nominal. For now, but appearances can deceive. 51 minutes into the flight, something happened that nobody talks about much in the official press releases. Communication dropped. Not degraded, not scratchy. Gone. NASA's Deep Space Network lost contact with Orion during a handover between satellites. The blackout lasted only minutes. Mission controllers maintained professional calm. They'd rehearsed this scenario. They had procedures. But procedures are written for expected problems. The handover failure wasn't expected. NASA Administrator Jared Isaacman addressed it briefly during a press conference. Temporary issue. Quickly resolved. Reason still being identified. Standard bureaucratic language that translates roughly to, "We don't actually know what happened yet." This matters more than it might seem. Communication isn't just about talking to the crew. It's about monitoring spacecraft health, detecting anomalies before they become emergencies, making informed decisions when seconds count. The crew experienced their first taste of isolation 51 minutes into a 10-day mission. That's concerning. Communication delays compound the isolation. Even when signals connect, they don't arrive instantly. Light speed sounds fast until you're trying to coordinate time-sensitive operations across 250,000 miles of space. 3-second delays don't sound like much. But imagine having a conversation where every response takes 3 seconds to arrive. Every question, every instruction, every emergency call for help. You can't have a real-time discussion with that kind of lag. You can't troubleshoot effectively. You can't provide immediate guidance when something goes wrong. The crew needs to function independently. They trained for this. But training in simulators on Earth differs fundamentally from actual deep space operations. Simulators can be paused. Instructors can intervene. You can reset and try again. Space doesn't offer reset buttons. Orion continues its journey. The spacecraft appears healthy. Systems functioning normally. Solar arrays deployed successfully after launch, generating more power than expected. That's good news. The power system performed well during Artemis 1 despite a minor anomaly in one of the power conditioning units. But Artemis 1 flew without crew, without a fully operational life support system, without the added complexity of 4 humans consuming oxygen, producing carbon dioxide, generating waste heat, and placing demands on every spacecraft system. Artemis 2 carries all that complexity, and the environmental control and life support system making its debut on this flight has already demonstrated problems on the ground. Controllers failed during pre-flight testing. Valves leaked. CO2 removal systems exhibited deficiencies. NASA addressed these issues before launch. They hardened circuits against excess voltage. They replaced deformed sealing materials. They validated fixes. But validation testing on Earth doesn't perfectly replicate the space environment. Microgravity changes how fluids behave. Temperature extremes stress materials differently. Vibration during launch can reveal weaknesses that ground testing missed. NASA built in a safety margin, that 24-hour checkout period in low Earth orbit before committing to translunar injection. The crew spent that time methodically testing every critical system: life support, navigation, communications, propulsion. Everything checked out. Flight controllers gave the go for TLI. The main engine fired. Orion climbed away from Earth. That decision committed the crew to a 10-day mission profile. No quick abort back to Earth. No emergency return within hours. The free return trajectory offers a safety net if propulsion fails, but it doesn't solve life support failures. It doesn't fix radiation shielding. It doesn't repair communication systems. The crew is past the point of easy rescue. Christina Koch dealt with the toilet controller issue earlier. That might sound trivial until you consider the implications. Waste management in microgravity isn't optional. It's essential for crew health and spacecraft habitability. A malfunctioning waste system could create serious hygiene issues. It could contaminate the cabin. It could make the spacecraft uninhabitable. Koch successfully troubleshot the problem. That's reassuring. It demonstrates crew competence under pressure, but it also reveals something unsettling. Even minor systems are experiencing glitches. If minor systems fail, what about major ones? The spacecraft is essentially a sealed can of complex machinery hurtling through the void. Every system depends on other systems. Power feeds life support. Life support enables crew survival. crew survival allows mission continuation. One significant failure could cascade. Redundancy helps. Critical systems have backups. Backups have backups. NASA engineers designed multiple failure paths into Orion, but redundancy isn't infinite. Eventually, you run out of backups. The battery issue discovered during abort scenario testing exemplifies this vulnerability. Late 2023 vibration tests revealed that batteries might disconnect during worst-case abort profiles. That would prevent parachute deployment. The spacecraft would be unable to land safely. Eagle Pitcher Technologies rebuilt and requalified the battery units. Problem solved, supposedly, but how many other edge cases remain undiscovered? How many failure modes lurk in the thousands of potential system interactions? Apollo 13 survived because of Eagle Pitcher batteries. Those silver-zinc cells were cold-soaked in space for days. They powered up when needed. They enabled re-entry. They saved 3 lives. Artemis II carries modern equivalents of those legendary batteries. But modern doesn't necessarily mean better. Sometimes it means more complex, more failure points, more things that can go wrong in ways nobody anticipated. The crew continues outbound. They're past equidistance now, more than halfway to the moon. The Earth shrinks behind them. The moon grows ahead. They've traveled further from home than any human in 54 years. Reed Wiseman commands from the left seat. Experienced astronaut, veteran of ISS operations, 6 spacewalks. He knows spacecraft systems. He's handled emergencies before. But never like this. Never this far from help. Victor Glover pilots from the right seat. Former Navy aviator, he flew Crew Dragon to ISS. He's logged time in space, but ISS orbits 250 miles up. Artemis II is traveling 250,000 miles out. Different magnitude, different risks. Christina Koch and Jeremy Hansen occupy the specialist seats. Koch brings her record-setting ISS experience. Hansen brings his CF-18 fighter background. Different skill sets, different perspectives. They'll need both. The crew practices procedures. They review emergency protocols. They monitor systems. They maintain readiness, but mostly they wait. Space travel involves long periods of waiting punctuated by brief moments of intensity. The lunar flyby approaches, Monday, April 6th. That's when intensity arrives. Orion will swing around the moon's far side. The spacecraft will enter the region where Earth disappears below the lunar horizon. Radio signals can't penetrate solid rock. The crew will be completely alone. No communication, no telemetry, no contact with mission control for approximately 40 minutes. 40 minutes doesn't sound long, but consider what can happen in 40 minutes. Apollo 13's oxygen tank exploded in seconds. Challenger was destroyed 73 seconds after launch. Columbia broke apart in 16 minutes. 40 minutes is an eternity when something goes wrong. The crew will rely on automated systems during the blackout, pre-programmed procedures, contingency plans, their own judgment and training. Mission Control will be watching telemetry data freeze as Orion disappears. Controllers will calculate when signals should resume. They'll watch the clock. They'll wait. Everyone will wait. This is the trade-off of deep space exploration. You gain incredible scientific value. You push human boundaries. You achieve historic firsts. But you sacrifice immediate support. You operate in an environment where help is measured in days, not hours. where communication blackouts are unavoidable, where isolation is absolute. The Apollo astronauts understood this. They accepted the risks. They flew anyway. Some came home with cataracts from cosmic ray exposure. Some experienced strange light flashes behind closed eyelids, high-energy particles streaking through their retinas. Some developed health issues years later that might have stemmed from radiation exposure. The Artemis II crew knows this history. They've studied Apollo mission reports. They've talked with surviving astronauts. They understand what they're volunteering for. But understanding intellectually differs from experiencing physically. Reading about radiation exposure isn't the same as feeling particles slam through your body. Studying communication blackouts isn't the same as sitting in silence while Earth vanishes behind the moon. The mission continues. Systems remain nominal. The crew appears healthy. Radiation exposure stays within predicted ranges. The solar weather remains quiet. That last point matters enormously. The Sun is currently in a relatively calm phase. No major coronal mass ejections. No significant solar particle events. That's fortunate. A massive solar storm during this mission would create serious problems. The crew trained to shelter during radiation events. They practiced removing equipment from storage bays, securing it around the cabin, adding mass between themselves and incoming particles. The procedure works in theory. It's never been tested in actual deep space conditions. If a major solar event occurs, they'll find out whether theory matches reality. The Moon to Mars. Space Weather Analysis Office monitors solar activity continuously. They share data with the Space Radiation Analysis Group. Together, they provide forecasts to flight controllers. Real-time measurements from inside Orion supplement their analysis. This gives mission control the information needed to issue recommendations. But recommendations require communication. If Orion is behind the moon when a solar event occurs, the crew won't receive warnings. They'll have to detect the radiation increase themselves using onboard instruments. They'll have to initiate shelter procedures without guidance from ground experts. Autonomous decision-making becomes critical. The crew can't wait for mission control approval during emergencies. They need authority to act independently. NASA granted them that authority. They're trusted to make life or death decisions without consulting Houston. That trust is necessary but uncomfortable. Space agencies prefer centralized control, ground-based expertise, careful deliberation before major decisions. Deep space operations make that preference impossible. The speed of light imposes delays. The moon blocks signals. The crew must be empowered. They're approaching the most critical phase now. The lunar flyby will test every system: navigation, propulsion, communication, life support, thermal management, power generation. Everything needs to work perfectly while the spacecraft whips around the moon. Orion's trajectory has been calculated with extraordinary precision. The spacecraft will pass within 4,000 miles of the lunar surface, close enough for detailed observations, far enough to maintain safety margins. The moon's gravity will bend their path. They'll slingshot around the far side. They'll emerge on a trajectory back toward Earth. If everything works as planned, the free return trajectory provides a safety net. But it's not foolproof. Apollo 13 proved that. Their spacecraft wasn't on a free return trajectory when the oxygen tank exploded. They had to execute a burn using the lunar module's descent engine to get back onto a safe path. That burn required new software written in real time by technicians at Mission Control. It required precise navigation without the usual reference points. It required the crew to manually control a spacecraft they'd barely trained to fly. Artemis II doesn't carry a lunar module. If they need to modify their trajectory, they'll use Orion's main engine. That engine needs to work. The navigation system needs to provide accurate data. The crew needs to execute burns precisely. Margins for error shrink dramatically in deep space. Near Earth, you can correct mistakes with subsequent burns. You have time, you have options. Beyond the Moon, options diminish. Time becomes precious. Mistakes compound. The crew understands these stakes. They're professionals. They're trained. They're ready. But ready doesn't guarantee safe. Ready doesn't eliminate risk. It reduces it. But reduction isn't elimination. The spacecraft is closing on the Moon now. Velocity building. Distance shrinking. Every second brings them closer to the moment where theory becomes reality. Mission Control watches telemetry streams. Hundreds of data points updating continuously. Temperature readings, pressure values, voltage levels, fuel quantities. Every system monitored, every parameter tracked. Looking for anomalies, searching for warning signs. The crew performs their own checks. Wiseman reviews navigation data. Koch monitors life support readings. Glover checks communication systems. Hansen verifies backup procedures. Redundancy built into every critical function. If one system fails, another takes over. That's the plan. Plans work until they don't. Apollo 13's plan didn't include an oxygen tank explosion. Columbia's plan didn't account for foam strike damage. Challenger's plan assumed O-rings would seal properly in cold weather. Plans represent best-case scenarios. Reality delivers actual scenarios. Artemis II's plan assumes the heat shield will perform adequately despite damage observed during Artemis I. That assumption carries the crew's lives. When Orion returns to Earth, when it slams into the atmosphere at 25,000 miles per hour, that heat shield needs to work, not perfectly, just well enough. The modified re-entry trajectory aims to reduce thermal stress. Instead of the skip entry used during Artemis I, Orion will follow a steeper profile, straight down, faster deceleration, shorter heating period, less time for internal pressure to build up in the AVCoat material. But steeper means harder. The crew will experience higher G-forces. Their bodies will be pressed deeper into their seats. Blood will pool. Vision might narrow. Consciousness could fade if the forces exceed tolerance limits. NASA calculated the acceptable range. The crew trained in centrifuges. They know what to expect. Knowing doesn't make it comfortable. The alternative was replacing the heat shield, building a new one, testing it thoroughly, delaying the mission by years. That option was rejected. Political pressure, schedule pressure, budget pressure. The decision was made to fly with what they have. Charles Kamada warned about this. Former astronaut, former NASA engineer. He saw the damaged heat shield photos. He reviewed the analysis. He reached a different conclusion than NASA's official position. Kamada argues NASA is repeating past mistakes, building models that confirm desired conclusions rather than revealing uncomfortable truths. Columbia's engineers built models showing foam strikes were acceptable. Those models were wrong. Challenger's engineers had data about O-ring problems. That data was dismissed. Is Artemis II's heat shield analysis similarly flawed? NASA insists it isn't. They claim extensive testing, rigorous analysis, conservative assumptions. They modified the trajectory to add safety margin, but the Artemis I heat shield lost material in more than 100 locations, deep gouges, complete loss of avcoat blocks in some areas. That damage exceeded all predictions. If predictions were wrong before, why trust them now? The publicly released report was heavily redacted. Critical details hidden. Former engineers and astronauts criticized the lack of transparency. If the analysis was solid, why redact so much? NASA applies different standards to different programs. When SpaceX Dragon or Boeing Starliner show problems, NASA demands fixes, redesigns, additional testing, unmanned validation flights. The commercial crew programs must meet rigorous safety requirements. Artemis doesn't face the same scrutiny. It's NASA's flagship program. It represents the agency's future. Admitting fundamental problems would mean massive delays, potential program cancellation, unacceptable political consequences. So the mission proceeds. The crew knows the risks. They accepted them. Astronauts always accept risks. That's part of the job. But accepting risk doesn't eliminate it. Orion continues its approach. The moon grows larger in the windows. The crew can see details now. Craters, mountains, the stark boundary between light and shadow. They're traveling faster than any humans have moved in 50 years. Faster than any humans alive have ever traveled. Apollo astronauts reached these speeds. They're all old now, or dead. The experience they gained is distant history. This crew is writing new history, or they're becoming a cautionary tale. The outcome depends on systems performing as designed, on calculations being correct, on assumptions being valid. The lunar flyby will test everything simultaneously. Navigation must be precise. Orion will pass within 4,000 miles of the surface, close enough for detailed observations, far enough for safety margin. That margin exists only if calculations are accurate. The moon's gravity is well mapped. Its mass is known. Its gravitational field is understood. But precision navigation requires accounting for subtle variations. Mass concentrations beneath the surface, irregularities in the gravitational field. These factors affect trajectory. Ground-based tracking provides position data. But there's delay. Light speed delay. Information about where Orion is takes seconds to reach Earth. By the time mission control sees telemetry, it's already outdated. The spacecraft has moved. Conditions have changed. During the lunar flyby, this delay becomes critical. Decisions need to happen fast. The crew can't wait for mission control approval. They need autonomy, authority to act. NASA granted that authority. Wiseman is commander. He makes final decisions. The crew trusts his judgment. Mission control trusts his judgment. Trust is necessary when communication takes seconds and circumstances change instantly. The spacecraft will disappear behind the moon soon. Communication will cease. 40 minutes of silence. 40 minutes where mission control sees nothing, hears nothing, knows nothing about the crew's status. During those 40 minutes, anything could happen. System failures, course deviations, emergency situations. The crew will handle whatever occurs without ground support, without expert consultation, without the comfort of knowing hundreds of specialists are watching their data. They'll be alone, truly alone, more isolated than any humans have been since Apollo 17. The far side of the moon blocks everything. Radio signals can't penetrate solid rock. Even if they screamed for help, no one would hear. The spacecraft is healthy right now. All systems nominal. No warnings, no anomalies. But systems can fail suddenly. Apollo 13's oxygen tank explosion happened without warning. One moment everything was fine. The next moment the mission was fighting for survival. Orion carries redundancy, backup systems for critical functions. If the main engine fails, reaction control thrusters can provide propulsion. If one battery dies, others supply power. If communication through one antenna is lost, others can transmit. But redundancy has limits. If multiple systems fail simultaneously, backups become overwhelmed. If problems cascade, redundancy collapses. Apollo 13 faced cascading failures. The oxygen tank explosion damaged multiple systems. Each failure created new problems. The crew had to improvise solutions using equipment that wasn't designed for those purposes. Artemis II doesn't carry a lunar module. Apollo 13 survived because the LM provided backup life support. It became a lifeboat. Its systems kept the crew alive, while the command module was powered down to conserve battery power. Orion stands alone. There's no backup vehicle, no lifeboat. If life support fails catastrophically, the crew has only their survival suits. Those suits provide breathable air for 6 days maximum. 6 days to get home. 6 days for mission control to devise solutions. 6 days before air runs out. The ECLSS already showed problems. Minor ones. Manageable ones. Christina Koch troubleshooted the toilet controller issue successfully. But that was a small problem. A single valve. A single controller. What if larger failures occur? The ECLSS made its debut on this flight. Artemis I didn't carry a complete life support system. This is the first time all components operate together in actual space conditions. Testing happened at the ground, in vacuum chambers, in simulated environments. But simulation isn't reality. The 24-hour checkout period in low Earth orbit was supposed to catch major problems. Orion remained close to Earth for a full day. The crew tested every system. They verified functionality. They confirmed readiness. Then they committed to the translunar injection burn. No turning back after that. Everything checked out. The ECLSS worked. Life support functioned. The crew pressed forward. They're committed now. They're beyond the point where Earth is an easy destination. If catastrophic ECLSS failure occurs now, the crew faces terrible choices. Try to repair it using whatever tools and materials are available. Ration air and water to extend survival time. Rush back to Earth on the fastest possible trajectory, accepting whatever risks that entails. The free return trajectory provides one option. Let the moon's gravity slingshot them homeward. Minimal propulsion required, conservation of consumables, maximum survival time. But free return takes days. Days of breathing, days of drinking, days of CO2 removal, days that require functioning life support. Apollo 13 stretched their consumables by shutting down non-essential systems. They endured cold, darkness, minimal power. They accepted discomfort to extend survival time. Could the Artemis II crew do the same? Their survival suits help, but suits are emergency equipment, temporary solutions, not designed for days of continuous use. They'll buy time. Maybe enough time, maybe not. The power system is another vulnerability. Solar arrays generate electricity. Batteries store it. Power conditioning units distribute it. Everything depends on electrical power, life support, navigation, communication, thermal control, propulsion, everything. During Artemis I, one power conditioning unit experienced an anomaly. It recovered. Systems continued functioning. But what if it hadn't recovered? What if the failure was permanent? What if multiple units failed? The spacecraft carries backup batteries, Eagle Picher silver zinc batteries, the same type that saved Apollo 13. Those batteries can provide emergency power, but only for limited duration. They're not designed to run the entire spacecraft indefinitely. Vibration testing revealed a frightening possibility. During extreme abort scenarios, batteries might disconnect. Physical disconnection. No electrical connection means no power. No power means no parachutes. No parachutes means no safe landing. That's a fringe scenario. It requires both SLS failure and maximum abort motor vibration. Unlikely combination, but unlikely isn't impossible. Columbia's foam strike was unlikely. Challenger's O-ring failure was unlikely. Unlikely events kill crews. NASA rebuilt the batteries, requalified them, strengthened connections, added redundancy. The problem should be fixed. Should be. Probably is. Almost certainly is. But certainly isn't absolute. The crew doesn't dwell on worst-case scenarios. They focus on procedures, on training, on the mission profile. Dwelling on disaster serves no purpose. Preparation serves purpose. They're prepared. They're approaching loss of signal now. The moon's bulk will block transmissions soon. The last communication window before 40 minutes of silence. Mission Control provides final updates. Trajectory looks good. Systems nominal. Weather at recovery site is acceptable. Everything proceeding as planned, Wiseman acknowledges. His voice is calm, professional, no hint of concern. The crew is ready. They've trained for this moment. They know what to do. See you on the other side, Wiseman says. Standard phrase, used since Apollo. Acknowledgement that they're about to disappear from view. Confidence that they'll reappear. Copy that, Orion. See you in 40, Capcom responds. Equally calm, equally professional. The routine exchange masks underlying tension. Everyone knows the risks. Everyone hopes for the best. The signal fades. Telemetry stops updating. The screens in Mission Control freeze on last known values. Everything looks good. Everything looked good for Apollo 13 too, right up until it didn't. Flight controllers settle in to wait. 40 minutes, 2400 seconds. Time measured in heartbeats and held breath. They watch the countdown clock. They review procedures. They prepare for reacquisition of signal. Behind the moon, the crew floats in silence. No communication with Earth. No reassuring voices from Mission Control. Just the soft hum of ventilation fans. The quiet beeping of systems monitoring themselves. The presence of 3 other humans in a very small space. They follow the timeline. Execute planned activities. Take photographs. Record observations. Collect data. The mission continues even without audience. Especially without audience. This is what they came for. The moon fills their windows now. Ancient surface, billions of years old, unchanged by wind or water, every crater preserved, every impact recorded in stone. The crew sees what no human has seen in 50 years. The far side in stunning detail. They're making history, or they're becoming history. The distinction depends on the next several days, on systems continuing to function, on calculations being correct, on luck favoring the prepared. 4 humans beyond Earth's protection, beyond quick rescue, beyond easy solutions. They chose this. They trained for this. They accepted the risks. Now they face the reality of those risks, alone behind the moon, trusting systems that have flown only once before. trusting a heat shield that failed its first test, trusting decisions made by people under immense political pressure. The flyby continues. Orion swings around the lunar far side. Gravity bends their path. Velocity increases. The trajectory is working for now. The minimum altitude is approaching. Closest approach to the lunar surface happens soon. 60 nautical miles above ancient craters, lower than any human since 1972. The crew watches through windows, grey landscape, harsh shadows, no atmosphere to soften edges. Wiseman activates the camera, high-resolution images for mission planners, data for future landing sites, scientific value, public relations value, proof they were here. Coke floats to the window. First woman this close to the moon. Historic milestone. Symbolic achievement. But symbols don't keep you alive. Systems keep you alive. She photographs Mare Tranquillitatis, the Sea of Tranquility, where Armstrong and Aldrin landed, where humanity first touched another world. The site looks impossibly small from here. Fragile. One tiny spot on a vast dead world. Glover monitors navigation data. Trajectory matches predictions within acceptable margins. Velocity correct. Altitude correct. Everything nominal. The moon's gravity is pulling them exactly as calculated. Physics working as advertised. Hansen checks life support readings. Oxygen levels stable. Carbon dioxide removal functioning. Temperature control maintaining cabin environment. The ECLSS hasn't failed yet. Hasn't proven Kamada's warnings. Hasn't vindicated NASA's confidence either. Just keeps working, for now. The far side passes beneath them, never visible from Earth. Radio silent, completely alone. No emergency rescue possible here. No quick abort. If something fails behind the moon, they handle it themselves, or they don't handle it at all. Mission Control can't help from Houston, can't see telemetry, can't monitor systems, can't offer advice. The crew is autonomous, self-sufficient, dependent only on their training and their spacecraft. Training prepares you for known problems, teaches procedures, builds muscle memory, but unknown problems don't follow procedures. They require improvisation, judgment, luck. The Apollo 13 crew had luck. Explosion didn't destroy command module. Lunar module still functional. Free return trajectory still achievable. Ground support could calculate solutions. Brilliant engineers could improvise fixes. Would Artemis II have the same luck? Would an explosion leave systems intact? Would the trajectory remain favorable? Would solutions exist for problems not yet imagined? Nobody knows, can't know, won't know unless it happens. The crew doesn't discuss these scenarios, doesn't verbalize fears. Professional astronauts maintain professional demeanor, calm voices, steady hands, focus on tasks. But everyone thinks about it. Impossible not to think about it. History teaches what can go wrong. Reality shows how fragile these machines are. Experience demonstrates that unlikely events occur. The flyby continues. Minutes pass. Systems continue functioning. Each minute without incident builds confidence, or maybe just postpones inevitable failure. Wiseman reviews the timeline. Next major event is Trans-Earth injection burn, 7 hours from now. The engine firing that sends them home. Critical maneuver, no backup if it fails. The main engine must fire, must burn for exact duration, must provide precise velocity change. Otherwise, they don't return to Earth. They drift into solar orbit, become permanent space debris with 4 dead astronauts inside. The engine worked during Artemis I, fired perfectly, met all performance specifications. But that was then. This is now. Different spacecraft, different conditions, different stakes. Engine reliability isn't guaranteed by previous success. Each firing is independent event. Combustion chamber could crack, fuel lines could leak, valves could stick, ignition could fail. NASA tested extensively, qualified the engine, certified it for flight. Same process used for Apollo, same engineering standards, same safety margins, same standards that approved Challenger's O-rings, same engineering that cleared Columbia's foam strike, same safety margins that failed catastrophically. Wiseman doesn't think about that, can't afford to think about that. He thinks about procedures, about timeline, about mission objectives, about doing the job he trained for. Koch photographs the lunar South Pole, future landing site for Artemis 3, where NASA plans to establish permanent presence, where water ice might exist in shadowed craters, where humanity might build lunar base. Ambitious plan, expensive plan, politically driven plan, built on foundation of Artemis 2 success. If this mission fails, those plans collapse, program ends, political support evaporates, the whole architecture falls apart. 4 lives carry the weight of entire program. Their survival determines NASA's future. Their success enables moon base. Their failure ends decades of planning. Nobody told them this explicitly, didn't need to tell them. They understand political reality, understand budget pressures, understand that programs die when crews die. Glover checks radiation dosimeter readings, exposure accumulating steadily, within predicted ranges. No solar events currently. Space weather remains quiet. The sun cooperates. For now. Solar storms are unpredictable, can erupt without warning. Plasma ejections traveling millions of miles per hour, arriving hours after initial flare, flooding spacecraft with radiation. The crew trained for this scenario, knows the procedures, pile equipment around sleeping quarters, create makeshift radiation shelter, wait out the storm, hope the shielding helps. But how much would it actually help? Unknown. Never tested with real solar event. Never validated with actual measurements. Theory says it works. Models predict effectiveness. Reality might disagree. Apollo astronauts got lucky, missed major storms, flew between dangerous events. Timing saved them, not planning, not engineering, just luck. Artemis 2 needs the same luck, maybe more luck. Staying in space longer than Apollo. More exposure time, more opportunities for solar events. Statistics work against them. Hansen monitors communication systems, getting close to reacquisition of signal. Soon they'll emerge from behind the moon, resume contact with Earth, end the isolation. The 40 minutes felt longer than 40 minutes. Time distorts in stress, stretches during uncertainty. Every minute wondering if systems will keep working. Every second watching indicators, waiting for warning lights, listening for unusual sounds. Nothing unusual happened. Everything functioned normally. Uneventful is good. Boring is wonderful. Routine is exactly what you want. The lunar limb approaches in windows. Earth about to reappear. Blue marble rising over grey horizon. Home becoming visible again. Connection restoring. Signal lock achieved. Telemetry streaming to Houston. Mission control sees their data again. Watches system status. Monitors health parameters. Orion, Houston, we have you back, Capcom announces. Relief evident in voice. Controlled relief. Professional relief. But relief nonetheless. Roger, Houston, good to hear you again, Wiseman responds. Same controlled tone. Same professionalism. Same underlying emotion. Flight controllers review data dumps. Everything nominal during loss of signal. All systems perform correctly. No anomalies detected. Successful flyby. The crew receives congratulations. Good job. Historic achievement. Farthest from Earth since Apollo. First woman beyond low orbit. Canadian astronaut reaching deep space. Milestones matter for history books, for press releases, for political speeches, for inspiring next generation. They don't matter for survival. Survival depends on next 7 hours going perfectly, depends on engine firing correctly, depends on trajectory calculations being accurate, depends on nothing unexpected happening. The crew begins trans-Earth injection preparations, review procedures, check systems, verify parameters. Everything by checklist, nothing left to chance, nothing assumed. Glover monitors propulsion systems, fuel pressures normal, helium pressurization stable, valve positions correct, engine ready for firing. Coke verifies navigation data, position confirmed, velocity measured, trajectory calculated, burn parameters loaded, computer ready to execute. Hansen checks life support one more time. Can't check too often. ECLSS still functioning, still providing air, still removing CO2, still maintaining temperature, still keeping them alive. Wiseman reviews abort procedures. What to do if engine fails. How to troubleshoot problems. When to shut down. When to try restart. Planning for failure while expecting success. The abort options aren't good. If trans-Earth injection fails completely, they're stuck. Free return trajectory only works if they're still on it. After flyby, they're committed. Engine must fire or they don't come home. Partial burn might be worse than no burn. Wrong trajectory. Wrong velocity. Miss Earth entirely. Or hit atmosphere wrong angle. Too steep means incineration. Too shallow means skip back into space. The margins are razor thin, mathematics unforgiving, physics doesn't negotiate. Either the numbers work or they don't. Apollo 13's engine fired perfectly when needed, brought them back, saved their lives. But that engine was different design, different fuel, different conditions. Not relevant to Artemis 2, except as reminder that engines can work when everything else fails, or reminder that engines matter, that single points of failure exist, that backup plans have limits. The countdown begins, T-minus 30 minutes to trans-Earth injection, half hour until commitment, until point of no return becomes literal. Mission Control provides final trajectory updates. Minor adjustments to burn parameters, optimization based on actual position and velocity, fine-tuning the numbers. Every decimal point matters. Every fraction of a meter per second affects landing location. Too much correction means splashdown wrong place. Too little means same problem. Recovery forces wait at predicted location. Ships positioned. Helicopters ready. Rescue swimmers standing by. Navy prepared for normal landing, also prepared for abnormal landing. Contingency plans for landing anywhere in broad ocean area, but contingency plans assume spacecraft survives re-entry, assumes heat shield works, assumes parachutes deploy, assumes crew alive to recover. T-minus 15 minutes, crew strapped into seats, helmets secured, suit pressures checked, ready for engine burn, ready for acceleration, ready for gravity forces pushing them into seats. The burn will last several minutes, steady thrust, building velocity, changing trajectory from lunar orbit to Earth intercept, mathematics made physical. Coke watches countdown timer, digital numbers decreasing, each second bringing them closer to commitment. Closer to home, closer to heat shield test, closer to finding out if NASA's confidence was justified, Glover's hand rests near abort button. Won't need it probably, but it's there, just in case. If engine shows problems, if thrust drops, if anything goes wrong during burn. Abort during trans-Earth injection creates nightmare scenario. Stuck in wrong orbit, wrong trajectory, limited options, all bad. T-5 minutes. Final systems check. Everything shows green. All parameters nominal. Spacecraft ready. Crew ready. Mission control ready. Hansen takes deep breath. Slow exhale. Controlling stress response. Managing adrenaline. Staying focused. Staying calm. Nobody talks. Nothing to say. Procedures complete. Checklist finished. Now they wait. Watch countdown. Trust systems. Trust engineers. Trust physics. T-1 minute. Longest 60 seconds of the mission. Longer than loss of signal. Longer than launch hold. Time stretching again. Each second individually experienced. Wiseman's finger hovers over manual abort. Won't use it unless absolutely necessary, but ready. Always ready. T-30 seconds. Computer controlling sequence now. Automated systems managing ignition. Humans monitoring, supervising, ready to intervene. T-10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Engine ignition. Thrust builds smoothly. Acceleration pushing crew into seats. G-forces increasing. Not violent, controlled. Exactly as predicted. Glover watches thrust indicator. Nominal. Engine performing correctly. Fuel flow steady. Chamber pressure good. Burn continues. 20 seconds. 30 seconds. Still nominal. Still perfect. Mathematics becoming reality. 45 seconds. Halfway through burn. Velocity increasing. Trajectory changing. Earth intercept path developing. 60 seconds. 3/4 complete. No problems. No anomalies. Engine doing exactly what it's supposed to do. 75 seconds. Almost finished. Final moments of burn. Critical seconds. 82 seconds. Engine cutoff. Burn complete. Perfect execution. Silence in cabin. Nobody speaks. Waiting for confirmation. Waiting for numbers. Mission control analyzes telemetry. Calculates actual trajectory. Compares to planned trajectory. Orion. Houston. Trans-Earth injection nominal. You're coming home. Relief floods through crew. Wiseman nods. Coke smiles. Glover exhales. Hansen grins. One major hurdle cleared. Engine worked. Trajectory correct. They're returning to Earth. But the hardest part remains. Re-entry awaits. Heat shield test awaits. 3,000 degrees awaits. The moment when NASA's decisions get validated or crew gets killed. 72 hours until that moment. 3 days to contemplate what's coming. 3 days to trust controversial heat shield. 3 days to wonder if they'll survive the fire. Entry interface -3 days. Orion coasts through void. Silent spacecraft. Sleeping crew. Earth growing larger in window. Blue marble expanding. Home approaching. Cock wakes first. Checks radiation dosimeter. Daily ritual. Numbers slightly elevated. Still within acceptable limits. Cosmic rays penetrating hull. Invisible particles passing through her body. Through her cells. Through her DNA. She doesn't think about long-term effects. Cancer risk years from now. Cataracts developing later. Apollo astronauts experienced both. Price of deep space exploration. Price she accepted when she signed up. Glover stirs, stretches in microgravity, muscles already weakening. 10 days insufficient for serious atrophy, but body changing nonetheless. Bone density decreasing, cardiovascular system adapting, fluid shifting toward head. They'll need help walking after landing. Medical teams standing by. Normal for returning astronauts. Even short missions require readjustment period. Hansen checks systems. Everything nominal. Life support functioning perfectly. No valve failures. No controller malfunctions. The 24-hour checkout in low Earth orbit proved critical. ECLSS performing exactly as designed. Temperature stable. Pressure stable. Oxygen levels good. CO2. Scrubbers working. Water reclamation operating. All systems green. Wiseman joins them. Quiet morning in spacecraft, if you can call it morning. Sun rises every 90 minutes in low Earth orbit. But they're not in low Earth orbit anymore. They're in cislunar space, between worlds. Sleep okay? Koch asks. Wiseman nods. Dreams about re-entry. Everyone dreams about re-entry. The moment approaching, unavoidable, inescapable. 3,000 degrees waiting, controversial heat shield waiting, NASA's confidence waiting to be tested. They eat breakfast, rehydrated food, not gourmet, but functional, calories needed, nutrition required, bodies preparing for ordeal ahead. Mission control established communication window, morning briefing scheduled, weather update expected, trajectory confirmation planned. Orion Houston, good morning. Morning Houston, ready for briefing. Weather looking favorable for primary landing zone. Backup sites also clear. Recovery forces positioned. USS Philippine Sea on station. Philippine Sea. Amphibious assault ship. Helicopters aboard. Rescue swimmers ready. Medical team prepared. Recovery operations planned down to smallest detail. Trajectory remains nominal. No correction burns required. Current path will bring you to entry interface as scheduled. Entry interface. The moment Orion hits atmosphere. The moment heat shield gets tested. The moment everything matters. 72 hours from that moment. 3 days. Counting down. Koch reviews procedures. Re-entry checklist memorized. But she reviews anyway. Repetition builds confidence. Confidence reduces stress. Stress management critical during high-risk operations. Service module jettison first. Explosive bolts separate modules. Service module burns up in atmosphere. Disposable hardware. One-time use. Then attitude control. Reaction thrusters orient heat shield. Precise positioning required. Shield must face incoming atmosphere. Must take full thermal load. Any misalignment could expose crew module sides. Could compromise protection. Could kill crew. Automated systems handle most of it. But crew monitors, ready to intervene. Ready to take manual control if needed. Glover studies telemetry. Spacecraft health data. All parameters nominal. Power systems functioning. Batteries charging properly. Solar arrays generating expected output. Those batteries, rebuilt after vibration testing, revealed potential disconnect during abort. Eagle Picture Technologies requalified units. Same batteries that saved Apollo 13. Legacy of reliability, but also legacy of learning from near disaster. Hansen checks communication systems. Multiple redundancies. Multiple frequencies. Multiple networks. Deep space. Network tracking them. Commercial satellites providing backup. Laser communication system tested earlier in mission. But none of that matters during blackout, when plasma forms around spacecraft during re-entry, when superheated gases block all signals, when crew becomes completely isolated from ground. 4 minutes of silence. 4 minutes mission control can't help. 4 minutes crew completely alone. 4 minutes trusting heat shield. Trusting trajectory. Trusting NASA's controversial decision. Wiseman thinks about those 4 minutes. thinks about plasma blackout, thinks about emerging from darkness, either alive or dead, either successful or catastrophic, no middle ground during re-entry. You think about Columbia, Glover asks quietly. Everyone thinks about Columbia. Damaged heat shield on launch, undetected damage, foam strike creating hole, hot gases penetrating during re-entry, spacecraft disintegrating, crew lost. Different scenario, Wiseman says. We know our heat shield condition. We know what happened on Artemis 1. NASA modified trajectories specifically to address it. Kamada doesn't think that's enough. Charles Kamada, former NASA engineer, former astronaut, vocal critic of decision to fly Artemis 2, argues agency repeating Columbia mistakes, building models to justify desired conclusion, flying on hope rather than data. Kamada doesn't have all the information, Wiseman says. Neither do we. Report was redacted. True. Publicly released version heavily redacted. Tiger Team findings partially classified. Specific details withheld. NASA citing proprietary concerns. Commercial sensitivity. National security implications. But also hiding uncertainty. Hiding risk. Hiding controversial decisions from public scrutiny. Koch interrupts. We accepted the risk. We trust the analysis. We're going home. Conversation ends. Nothing more to say. Decision made. Trajectory set. Re-entry approaching. Entry interface minus 48 hours. Earth dominates window now. Beautiful planet. Blue oceans. White clouds. Brown continents. Home world. Fragile ecosystem. Pale blue dot. From this distance, you can't see borders. Can't see nations. Can't see conflicts. Just one planet. One humanity. One shared home. They've traveled farther from Earth than any humans in 50 years. Seen Moon up close. Experienced deep space. Crossed boundary Apollo astronauts crossed. Joined exclusive club. But now they want home. Want gravity. Want air without recycling. Want horizon that doesn't curve sharply. Want sky that isn't black. Mission Control provides update. Artemis 2, Houston. Entry trajectory confirmed. Interface in 47 hours, 32 minutes. Weather remains favorable. Copy Houston, 4732 to interface. Koch performs final equipment checks. Survival suits inspected. Helmets tested. Pressure seals verified. Communications confirmed. Every system scrutinized. These suits keep them alive if cabin depressurizes. Provide breathable air. Remove CO2. Maintain temperature. Protect during splashdown. 6 days survival capability. More than enough for recovery operations. Glover reviews landing procedures. Water landing different from runway landing. Shuttle landed on concrete. Orion lands in ocean. Capsule designed to float. Stable in multiple orientations. Rescue swimmers attach flotation collar. Helicopter recovery lifts crew out. Unless something goes wrong. Unless parachutes fail. Unless capsule sinks. Unless crew injured. Unless recovery delayed. Contingency plans exist for everything. NASA learned from Mercury, from Gemini, from Apollo, from Shuttle. 60 years of lessons, 60 years of close calls, 60 years of occasionally fatal mistakes. Hansen thinks about those mistakes. Challenger, Columbia, Apollo 1, Soyuz 1, Soyuz 11. Long list of disasters. Each one teaching lesson. Each one changing procedures. Each one paid for with human lives. Will Artemis 2 add to that list? Or prove NASA learned lessons? Prove modified trajectory works? Prove heat shield adequate? 48 hours until answer. Entry interface minus 24 hours. Final day. Final checks. Final preparations. Crew compartment feels smaller now. 10 days together. Confined space. limited privacy, psychological pressure building, normal for long-duration missions, manageable but present. They've handled it well. Professional astronauts, trained for isolation, trained for confinement, trained for interpersonal stress. But training doesn't eliminate it, just makes it manageable. Mission Control schedules final conference. Administrator wants to speak with crew. Public relations opportunity. Inspiring moment. Historic achievement. But also possible final communication. If re-entry fails. If heat shield fails. If crew dies. Last words preserved. Last message recorded. Artemis 2. This is Houston. Administrator on the line. Go ahead, Houston. Crew of Artemis 2, you've accomplished something remarkable. First humans beyond low Earth orbit in half a century. You've tested systems, proven capabilities, paved way for Artemis 3 lunar landing. The world watches. The world waits. We're ready to bring you home. Wiseman responds. Thank you, sir. We're ready. See you tomorrow. Professional, confident, calm, exactly right tone. No fear, no doubt, no hesitation. But fear exists. Doubt exists. Hesitation exists. Hidden beneath professional exterior, controlled but present. They secure equipment, stow loose items, prepare cabin for re-entry forces. Everything must be restrained. Anything loose becomes projectile during deceleration, could injure crew, could damage systems. Coke double checks heat shield orientation procedures, reviews manual backup, studies contingency plans. Preparation reduces anxiety. Control reduces fear. Glover reviews medical supplies, emergency equipment accessible, trauma kit ready, medications available. Hope to never use them, but ready if needed. Hansen performs final systems check. Power levels good. Battery charge optimal. Fuel reserves adequate. Reaction control propellant sufficient. All consumables within limits. Wiseman updates flight plan. Timing critical. Entry angle critical. Too steep and deceleration kills them. Too shallow and they skip off atmosphere. Goldilocks zone narrow. Margin for error small. NASA calculated precisely. Modified trajectory accounts for heat shield concerns. Steeper entry profile. No skip maneuver. Straight plunge into atmosphere. Shorter downrange landing. Higher G-forces. But supposedly safer for heat shield. Supposedly. Based on analysis. Based on models. Based on extrapolation from Artemis 1 damage. Based on Tiger team conclusions. Based on redacted report. Based on NASA's confidence. Entry interface -12 hours. Sleep scheduled. Rest required. Bodies need recovery. Minds need break. Re-entry demands full alertness, full capability, full performance. But sleep difficult. Minds racing, hearts pounding, adrenaline building, natural stress response, evolution preparing them for danger. Coke lies in sleeping bag, eyes closed, breathing controlled, meditation techniques, stress management, mental preparation. She thinks about heat shield, thinks about AVCOAT material, thinks about internal pressure, thinks about cracking, thinks about uneven shedding, thinks about 100 locations where material liberated during Artemis 1 re-entry. She thinks about NASA's solution. Modified trajectory, steeper entry, elimination of skip, supposedly minimizing char loss, supposedly providing adequate thermal margin, supposedly. Glover also awake, also thinking, also worrying. He thinks about his family, thinks about home, thinks about seeing them again, thinks about possibility of not seeing them again. Space exploration requires sacrifice, requires risk acceptance, requires willingness to die for advancement of knowledge, for expansion of humanity, for dreams of exploration. But willingness doesn't mean desire. A Acceptance doesn't mean eagerness. They want to live, want to return, want to survive fire. Hansen reviews procedures mentally, each step memorized, each action planned, each contingency considered. Mental rehearsal proven effective, visualization improving performance, preparation building confidence. Wiseman lies still, breathing steady, appearing calm, but mind active. Commander responsibility heavy, crew safety his priority, mission success important. But crew safety paramount. He thinks about decisions, thinks about NASA's choice, thinks about flying without redesigned heat shield, thinks about commercial crew standards, thinks about double standards, thinks about political pressure, thinks about schedule pressure, thinks about budget pressure, thinks about crew in his care. Entry interface -6 hours. Wake-up call from mission control. Final preparations begin. Suits donned. Systems activated. Checklists executed. Earth fills window completely now. Massive sphere. Destination visible. Home close. But barrier remains. Atmosphere remains. Heat shield test remains. Artemis II, Houston. Entry interface in 6 hours. All systems go for re-entry. Copy, Houston. We're ready. Final meal consumed. Last food before landing. Calories needed. Energy required. Bodies preparing for stress. They don helmets. SEAL suits. Check pressures. Verify communications. Each astronaut becomes self-contained system. Protected. Isolated. Independent. Service module jettison scheduled for interface -30 minutes. Explosive separation. Final commitment. No abort possible after jettison. They're committed to re-entry, committed to heat shield, committed to NASA's confidence. Coke watches countdown timer. Numbers decreasing, each second bringing them closer. Closer to fire, closer to plasma, closer to finding out if they survive. Entry interface -1 hour. Wiseman takes manual control, automated systems ready, but commander monitoring, ready to intervene, ready to adjust, ready to react. Glover monitors trajectory, perfect alignment, exact entry angle, precise timing, mathematics made physical, calculations made real. Hansen checks life support final time. Oxygen good, pressure good, temperature good, everything nominal, everything ready. Coke's hand rests near abort trigger. Won't help now. Too late for abort. But instinct keeps hand there. Training keeps hand ready. Entry interface -30 minutes. Artemis II. Houston. You are go for service module SEP. Copy, Houston. Go for SEP. Wiseman arms explosive bolts. Hansen confirms ready. Coke monitors systems. Glover watches countdown. T-10 seconds to separation. 9, 8, 7, 6, 5, 4, 3, 2, 1. Explosive charges fire. Service module separates. Tumbles away. Begins death dive into atmosphere. Will burn completely. Will leave no trace. Orion alone now. Crew module only. Heat shield exposed. Facing destiny. Facing fire. Facing test. Entry interface. -15 minutes. Attitude control thrusters fire. Rotating capsule. Positioning heat shield. Precise orientation required. Computer controlling. Crew monitoring. Earth rushing closer. Atmosphere approaching. Invisible boundary ahead. Kármán line. Edge of space. Threshold between void and air. Entry interface -5 minutes. Final systems check. Everything green. All parameters nominal. Spacecraft ready. Crew ready. Heat shield ready. Or so NASA believes. Entry interface -1 minute. Longest 60 seconds. Time stretching. Each heartbeat individually counted. Each breath consciously taken. Coke grips armrests. Glover closes eyes briefly. Hansen swallows hard. Wiseman watches displays. T-minus 30 seconds. Atmosphere ahead. Molecules waiting. Friction waiting. Heat waiting. 3,000 degrees waiting. T-minus 10. No turning back. No escape. Only through. Only survival or death. Only success or catastrophe. 5, 4, 3, 2, 1. Entry interface. First molecules hit heat shield. Friction begins. Temperature rises. Avcoat starts ablating, exactly as designed. Material sacrificing itself, carrying heat away, protecting crew. G-forces building, deceleration increasing, bodies pressed into seats. Modified trajectory means higher Gs. Steeper entry means harder forces, but forces tolerable, within human limits. Uncomfortable, but survivable. Heat shield glowing now. Orange, red, white, incandescent. Plasma forming around capsule. Superheated gases. Ionized particles. Radio blackout beginning. Houston, Orion. Entering blackout. Last words before silence. Last communication before isolation. 4 minutes alone. 4 minutes trusting heat shield. 4 minutes hoping NASA right. Plasma envelope complete now. Spacecraft surrounded. Glowing cocoon. Beautiful and terrifying. Fire outside windows. Orange light filling cabin. Temperature inside rising slightly. Heat conducting through hull. Not dangerous. Not unexpected. But noticeable. Reminder of inferno outside. G-forces peak. 6 Gs, 7 Gs. Bodies heavy. Breathing difficult. Vision narrowing. Blood draining from heads. Training prevents blackout. Conditioning maintains consciousness. Heat shield performing. Ablating correctly. Charring predictably. Material shedding, but evenly this time. Controlled this time. Modified trajectory working. NASA's confidence justified. So far. Peak heating passing. Temperature decreasing. Plasma thinning. Radio signals penetrating. Blackout ending. 4 minutes elapsed. Longest 4 minutes. Eternal 4 minutes. But survived. Heat shield held. Avcoat worked. NASA right. Orion, Houston, how do you read? Beautiful words, most beautiful words. Communication restored. Connection re-established. No longer alone. Houston, Orion, loud and clear. Heat shield performed nominally. Relief floods mission control. Applause erupts. Controllers celebrating. Engineers vindicated. Critics silenced. But re-entry continues. Parachute deployment ahead. Water landing ahead. Recovery ahead. Still dangerous. Still critical. Not finished yet. Drogue chutes deploy. Small parachutes stabilizing descent. Slowing fall. Preparing for mains. Main parachutes deploy. 3 massive canopies. Orange and white. Billowing above capsule. Slowing descent to safe landing speed. Ocean visible below. Blue water. White caps. Recovery ships waiting. Helicopters circling. Rescue swimmers ready. Final moments of flight. Final seconds of mission. 10 days in space ending. Historic flight concluding. Splashdown. Impact gentle. Water cushioning landing. Capsule floating. Stable orientation. Crew safe. Mission successful. Recovery swimmers deployed immediately. Flotation collar attached. Capsule secured. Helicopter approaching. Hatch opens. Fresh air enters. Salt smell. Ocean breeze. Earth atmosphere. Home air. Coke emerges first. Helped into rescue basket. Lifted to helicopter. Legs weak. Gravity heavy, but alive. Smiling. Successful. Glover next. Then Hansen. Finally Wiseman. All 4 recovered. All 4 healthy. All 4 home. USS Philippine Sea Deck ahead. Medical team waiting. Debriefing scheduled. press conference planned, celebrations prepared. But first, just breathing, just feeling gravity, just being home, just being alive. Artemis 2 complete, heat shield tested, controversy resolved, NASA vindicated, crew safe, the fire survived, the gamble won, the mission accomplished, and somewhere, engineers already planning Artemis 3, already designing lunar lander, already preparing for actual moon landing. Building on this success, learning from this mission, advancing towards sustainable lunar presence. Because this was never just about flying around moon, never just about testing hardware, never just about proving capabilities. This was about returning to deep space, about rekindling exploration, about preparing for Mars, about expanding human presence beyond Earth. Artemis 2 proved it possible, proved heat shield adequate, proved systems reliable, proved crew capable. The fire didn't kill them, the risk didn't destroy them, the controversy didn't stop them. They flew through hell at 3,000 degrees and emerged intact. They trusted NASA's confidence and survived. They became first crew beyond low Earth orbit in 50 years and returned safely. The mission everyone said was too dangerous. The heat shield everyone said would fail. The gamble everyone said wasn't worth taking. All wrong, all proven wrong, all silenced by successful splashdown. Artemis 2 complete, crew safe, moon program continuing, future secured. The fire has been survived. 4 astronauts floating in Pacific Ocean, helicopter rotors beating overhead, recovery swimmers securing capsule, USS Philippines Sea approaching, mission successful, crew alive, heat shield held. The fire has been survived once, will be survived again and again and again, until it isn't.